So thank you for coming to my talk. I've had the opportunity to work with Mirella and Susan Buchheimer and Shula Green at UCLA, and we're looking at thalamic GABA to glutamate ratio as measured by MRS, and how it's related to intrinsic brain connectivity and sensory overresponsivity in kids with autism spectrum disorder. Sensory overresponsivity, or SOR, is extremely common in autism, with rates as high as 70%, and it's also seen in typically developing youth, but at lower rates, maybe as high as 17%. And then at rates somewhere in between, we have kids that have ADHD, other anxiety disorders, and a history of trauma or early life stress. And sensory overresponsivity is characterized by a negative reaction to or avoidance of sensory stimuli that would not be considered aversive to most people, such as tags in clothing or certain kinds of sounds. And sensory overresponsivity is very impairing for the people who have it. In autism, we see that it's related to greater autism symptom severity overall and worse functional impairment. So in our lab, previous studies have shown that sensory overresponsivity severity correlates with neural activation in certain areas during a task where the kid in the scanner is experiencing a tactile and auditory stimulus at the same time than compared to baseline. And those areas are the amygdala, the thalamus, and the auditory and somatosensory cortices. So we've been looking at the thalamocortical and subcortical networks to understand how these might be involved in sensory overresponsivity. We know the thalamus is part of the sensory system and the salience network and is involved in integrating, relaying, and inhibiting attention to sensory information. And an important part of that are the thalamocortical, striatal, thalamo loops that the thalamus plays a role in. And then also the amygdala is part of the limbic system, and it's involved in emotional learning and responses and memory. So our group has found that the thalamocortical connectivity during sensory stimulation is different in kids with ASD compared to typically developing youth. And in particular, we see that in the typically developing youth, there is a increase during sensory stimulation in the frontal cortex, the visual cortex, auditory cortex, and some other frontal cortical areas. And then there's a decrease, you can see in the bottom right here, during sensory stimulation in some of the somatosensory areas. But in the autistic youth, in the lower right corner of the figure, or lower left corner of the figure, you can see that overall there's just less modulation of the thalamocortical connectivity during sensory stimuli. Also in the ASD youth, the thalamoamygdala connectivity is correlated with the severity of the sensory overresponsivity symptoms. So in this same group, it was found that their sensory overresponsivity score, where a greater number is worse impairment, was correlated with a greater thalamoamygdala connectivity. And these results together suggest that there is an imbalance between the cortical-thalamic activity and the thalamoamygdala connectivity in the kids with sensory overresponsivity. And perhaps that this imbalance could be related to the deficits in selective attention that are seen in autism, and that could be related to SOR. So to think about the imbalance, we started to think about what is considered the inhibitory and excitatory ratio hypothesis in autism. GABA and glutamate are the major inhibitory and excitatory neurotransmitters of the CNS, respectively, and very prevalent. GABA at 35% of synapses and glutamate at as much as 90% of synapses. And there's been a number of lines of evidence that have suggested that there's alteration in the inhibitory excitatory ratio in ASD. For instance, seizures are commonly comorbid with autism. There has been found to be a decreased GABA receptor subunit concentration in ASD. There is less of GAD, the enzyme that produces GABA from glutamate in ASD. And theories have been proposed namely by Rubenstein and Merzenich, about how a decreased inhibitory-excitatory ratio might lead to decreased lateral inhibition, which would cause potentially less specific tuning, so that cortical mini-column development might be altered or disrupted during critical periods. And that is given as an explanation for why we might have both sensory over-responsivity, under-responsivity, and other kinds of sensory abnormalities in autism. So we sought to understand how this inhibitory to excitatory ratio might be related to thalamic connectivity in kids with autism and sensory over-responsivity. Our preliminary group consists of 23 youth with autism, 13 typically developing youth, and our behavioral measures that I'm showing here are of sensory over-responsivity, where importantly the higher score is worse sensory over-responsivity impairment. We used a magnetic resonance spectroscopy voxel placed in the bilateral thalami crossing the midline, and we used a Siemens megapress sequence with post-processing in MATLAB. The resting state fMRI analysis used the bilateral thalamus as a seed in whole brain connectivity analyses, and we used the thalamic GABA to glutamate ratio as a regressor to determine how the GABA concentration predicted thalamic connectivity. So here you can see our MR spectra. So on the left we have a normal proton spectrum where the frequency selective pulse is off. In the megapress sequence, you use an on and off frequency selective pulse, and when you subtract them, you get the spectra that we see on the right here, and the peaks that come out are GABA and glutamate respectively, and by measuring the area of those peaks, we can get a measure of the metabolite concentration. And in the upper left corner, you can see that our voxel is placed right on the thalamus and it crosses the midline. So in our sample, interestingly, we found that there was no difference in the mean GABA to glutamate ratio between the autism spectrum disorder youth and the typically developing youth, although we only have 13 TDs and we're working on that number. But we did find that worse sensory over-responsivity is correlated with lower thalamic GABA to glutamate ratio in autism spectrum disorder. And so what you see here is that, no, that's not right. Okay. What you see is that in the lower GABA range, so towards the left side of the graph, that the sensory over-responsivity is worse, where they have lower inhibitory tone. So then looking at the bilateral thalamic seed connectivity, just without any regressors first, we see that the thalamus is connected with itself, with the amygdala, with the striatum and putamen, with the anterior cingulate cortex, and then we added the thalamic GABA to glutamate ratio as a regressor. And there's two things you can see here. One is that the areas that the thalamic GABA to glutamate ratio have greater positive connectivity with the bilateral thalamus are very much the same areas that we see that the thalamus is connected to generally. And then also that these are areas that are important for sensory modulation. So our lab has previously seen that the right orbitofrontal cortex, the bilateral amygdala, the bilateral putamen, the bilateral cingulate gyrus, and the thalamus, within the thalamus, are important areas for sensory modulation. So in conclusion, from this data, we can see that the lower GABA to glutamate ratio, or lower inhibitory tone, is associated with greater SOR severity and less resting state connectivity between the thalamus and critical areas involved in modulating response to sensory input. And this supports our group's theory that SOR is related to a change in the salience potentially of sensory information for kids with ASD. I'd like to thank my mentors and the people in my lab, and thank you so much for listening to my talk.